And with that, let's turn our attention to the last, but certainly not least, talk of the workshop. So please take it away when you're ready.
Yeah. Hi, hello. Yeah. Hi, hello everyone. My name is Brant. I'm a second-year PhD student at UIUC. I'm presenting the Poseidon framework for profile-guided numerical rewriting at full application scale. This is joint work done in collaboration with Vimarsh, Sathia, Ivanov, Jan Hueckelheim, Paul Hovland, and my advisor William Moses. So it is always desirable to make a piece of numerical software faster and more accurate. However, optimizing practical numerical code is often challenging at 3 levels: context, scope, and skill. By the end of this talk, I hope to convince you that profiling and compiler optimization are the key to address all 3 challenges. So first of all, context is really important when doing numerical rewriting. In this simple code example where we accumulate a nonlinear operation to a running sum, in this example, if we were to lower the nonlinear operation to use float, that is also known as single precision floating point numbers, we get a 1.6x speedup with a relatively small error, that's 1 in minus 12. That's in general safe. But if we go further a step by lowering the running sum to using float, the error can bump to 1 in minus 4. That's often risky for an application. This is something that can be exposed using profiling within the compiler. By just running 10 iterations of this loop, we can find that the reduction here is 10kx more sensitive than the nonlinear operations to such kind of precision changes. We propose a structured critical value hypothesis. The values that's critical to accuracy of the entire program are often structural. For example, there are certain kinds of computation like reduction, cancellation, one-hot vector, thresholds, that's very structural, and even a small surrogate profile can reveal the key information needed to do numerical rewrites. And there's another challenge called scope. Precision is just one possible rewrite. There are also other kinds of rewrites that may be better for a piece of program. For example, in this expression, we add a big number to a small number minus another big number. If we were doing using FP32, we can get the +1 rounded away because we have only 23 mantissa bits, and we get a wrong result, 0. And one obvious fix is to invest more mantissa bits to it. By using FP64, and the +1 will survive under this precision, and we hit a fundamental performance accuracy trade-off because we have to pay more runtime cost to using a higher precision like FP64. And there is a different class of rewrites called algebraic rewrites that can circumvent this trade-off, but doing this requires expertise, and for things to be correct, because you can do some like Taylor expansion that can be wrong for some inputs, and also requires some program analysis for the rewrite to be profitable in terms of performance. And there's a third challenge called scale. For a practical application, for example, this simple foo function, that's written in C. The mass can be hidden behind a bunch of complexity, for example, control flow. For example, there can be memory loads and stores. There can be function call boundaries that make a lot of existing source or binary level tools fail because they cannot see through these complexities. So our key insight here is that a production compiler has the exact necessary machinery to circumvent this challenge because there are standard LVM passes, for example, mem to reg, that converts the memory loads and store into an infinite register form. And there we can also do some control flow graph simplification to eliminate some control flow branches to fold them into a select instruction that so we get a straight line program, and we can also do inlining to fold this foo function to its surrounding context. So in this example, if we do inlining, we know the caller wants this max expression by calling this foo function. So we hope to answer two key scientific questions here. Question number one, can we automate advanced numerical rewriting techniques, including algebraic rewrites, in compilers? And there's a second question. How much performance are we actually leaving on the table due to suboptimal choices of precision and expressions in the real application? We built Poseidon to answer these two questions, and Poseidon is the first framework that automates advanced numerical rewriting techniques within the production compiler. It operates as a two-phase compiler. In the first compilation, we instrument user program to collect the numerical context necessary to perform context-sensitive rewrites, like the reassociation we shown in an early example. And in the second compilation, we perform the full application scale numerical rewrites in the following stages. First, more details on the profiling pass. We perform pre-optimizations that's actually standard LVM passes to expose underlying mass. So the compiler can see more context of the numerical program. And we generate runtime profile, including execution counts, running sum of values and gradients per floating point instruction. And we then do subgraph extraction to get expression graphs through a linear time flow scan of LVM intermediate representation of the application, and expression graphs are used to synthesize numerical rewrites. We synthesize these numerical rewrites in a candidate generation phase. We have multiple classes of rewrites. So class number one, we can do algebraic rewrites by using external tools called Herbie. That's based on equality saturation, and we can also propose expression graph precision changes in this phase. And this phase is also follow extensible to a broader scope of rewrites. In particular, we invoke Herbie to generate floating point expression rewrites. We as a compiler can identify LVM expression graphs that's supported by Herbie to do rewrites, and we can use compiler optimization to make this subgraph larger by including more numerical context, so Herbie can perform more effective rewrites. Poseidon can also be the compiler substrate for other tools because within the compiler, we can see more numerical context. And in this example, the Poseidon can construct this Herbie input expression by injecting the profile bounds into the FP core expression as preconditions, and call Herbie to generate a bunch of expression rewrites. And then having a bunch of expression rewrites or precision changes candidates at hand, we want to evaluate the candidate rewrites performance accuracy impact on the entire large-scale application. We use two two models, a performance cost model. For example, we perform micro benchmarking on LVM floating point instructions to assign them integer costs, and we sum up the affected instructions per instruction cost as a cost measure of the rewrite, and we can also evaluate their accuracy implication by sampling random inputs from the profile bounds and compute a local error using a high precision MPFR arbitrary precision float as a reference, and multiply with a profiled global sensitivity measure over affected instructions to get a global accuracy measure. And having a bunch of rewrite candidates evaluated in terms of cost and performance, we can use a DP solver to evaluate a Pareto frontier with a bunch of performance accuracy trade-off. As a result, for any given cost accuracy budget, Poseidon can have the best rewrite strategy according to the performance accuracy model. And we evaluate Poseidon on multiple large-scale applications. For example, here's a quaternion differentiator. The original program is the red triangular symbol on the lower right corner, and it's using floating point 64, and it's fairly accurate, and we can generate these blue dots as the rewrite as the optimized programs, composing rewrites in different ways. And this yellow star has a 1.46x speedup at a cost of a higher error, and we can also use a lot of accuracy improving Herbie rewrites to reduce the error by 27% by paying more compute time. And here's a particularly interesting result. We can apply Poseidon on a large DOE proxy application that's more than 5,000 lines of code with 200 loops. And the original program has 12 UOPs away from a highly accurate MPFR reference result. And Poseidon can automatically apply 9 algebraic rewrites. That's fairly complicated to achieve an optimal FP64 error with no substantial slowdown. And there are also existing ways to get more accurate results. For example, there's hardware accelerated FP80 that takes more than 6x more runtime, but still being 2 UOPs away from the ground truth. We can also use software emulated libraries. For example, we can use 74 mantissa bits floating points using MPFR, and the runtime is at least 500 times more than a native floating point. And we have an ongoing work of applying Poseidon to rewrite accelerator code. They're fully leveraging an arithmetic throughput of an accelerator is challenging for multiple reasons. First of all, most of the flops of an accelerator are in specialized hardware instructions, for example, a tensor core, and raising scalar operations into tensor core operations requires expert analysis. And there is a recent trend of deprioritizing high precision. For example, in new NVIDIA GPUs, FP64 runs at only 1/64th the rate of FP32, and the GPU has a very different cost model. Because of this, instead of using native FP64, it may be sometimes faster to emulate high precision arithmetic with lower precision floats, for example, FP16. And we want to answer this question here: can we automatically choose the right rewrite strategy for a practical accelerator code while still satisfying an application level accuracy target specified by the user? And we find that Poseidon's profile-guided optimization approach is an answer to this question. We extended the Poseidon's candidate generation phase with floating point emulation techniques. For example, for scalar operations, we can do multi-float by composing multiple scalar precision floating point numbers using lower precision numbers to emulate a higher precision, or we can do multiple lower precision matrix multiplications to emulate a higher precision matrix multiplication using Ozaki scheme. And we can also propose raising rewrites to raise scalar operation into tensor core operations, given a user-specified accuracy target that can differ across application and across scientific domains. Poseidon can solve for the right rewrite strategy. And we applied Poseidon to an astronomy application that's GPU accelerated. Herbie and multi-flow rewrites can make things 4.4x faster while still having a near FP64 accuracy. And we can also automatically raise an insensitive matrix product within an eigensolver to use TF32 tensor core operation that previously required expert analysis to understand which scalar operations are matmos and are less sensitive to such precision reduction. And we also applied Poseidon to a chemistry software. There is a scientifically meaningful threshold in literature for this application, and given this user-specified accuracy target to produce scientifically meaningful results, Poseidon can automatically raise some scalar operations to tensor core and materialize Ozaki scheme to improve to achieve a near FP64 accuracy while being 4.46x faster and about 2 times faster than a Kubla's dense general matrix multiplication. And this concludes my talk. I introduced Poseidon, which is a profiling and compiler optimization approach to provide context, scope, and skill needed to perform numerical rewrites of large-scale applications. And we can do automated numerical rewrites at full application scale within the compiler. And recently, we extended Poseidon to enable fast and accurate accelerator code automatically within the compiler. Thank you.
Okay, thank you so much. We have time for a few questions.
I wonder if you've considered the alternative standard for approximate numerical representations called POSIT, standard POSIT 22, and if that compares to, if you've done any comparisons on that, I'd be curious.
We actually talked with the professor who proposed that, POSIT numbers are very interesting and absolutely can be integrated to our candidate generation phase. We can propose rewrites to use POSIT numbers instead of the regular IEEE floats. That's a future direction we are happy to explore.
So I think from EGRAPHS' rewrite point of view, there's kind of this interesting thing going on where inside Poseidon, you have this sequencing where you do LLVM-based rewrites, then you do a rewrite suggested by Herbie, and then you do some kind of, you said, dynamic programming style extraction to pick the best speed accuracy trade-offs. And then within Herbie itself, there's also an eGraph that's also sequencing a bunch of rewrites to propose the candidates. So I guess what I'm curious about is, it clearly seems to work, but is this just a pragmatic design, or is there something important going on here where the LVM-based rewrites need to be sequenced before some of the Herbie-based ones? Is there some wisdom in this schedule where we've got different kinds of rewrites that apply at different times and multiple levels of extraction, or is this just a pragmatic convenience from Herbie was already available?
It is true that Herbie do have this kind of soft within it, and there are a lot of complexity in practical application to prevent us from just relying on a Herbie-style internal soft, because there can be multiple expression subgraphs scattered across the entire program that may have different kinds of sensitivity, that we need a global kind of Poseidon-style soft at the end after Herbie's internal soft for each intermediate subgraphs.
Thank you.
Yeah.
So please correct me if I'm wrong, but for your profiling is guided by a first order approximation of floating point error, right?
Yeah.
So a problem with first order approximation of floating point error is the model. So another important part of floating point is overflows and underflows, and overflows and underflows, nans, stuff like that is out of model with your first order error approximation stuff. My favorite example is an expression square root of 1 plus x square, where if x is very large, in floating point this will overflow, but the actual the actual answer to square root of 1 plus x square is representable in floating point. So do you care about errors like this? Is this something that you want to fix?
There are multiple ways to fix it. For overflow or underflow, this frequently happens, especially for accelerator code, because the range of supported floats can be really small. If it's only 16-bit of a float, we can assign a large constant as a penalty to that kind of overflow behavior. There are also a way to extend Poseidon's soft or profiling phase with the more advanced or I should say more faithful approximation instead of the linear approximation we applied here. That's totally doable in profiling phase.
Okay, let's thank the speaker one more time.